Hi there. Okay, in this video we're going to look at some more examples using our basic differentiation rules that we learned in the last video. And if you didn't see the last video, I'll recap those rules for you really quick. The first rule we looked at was our constant rule. It just says that the derivative of a constant is 0. And we looked at some examples here. The second rule was our power rule. The third rule was this rule that says if you have a constant multiplied by a function, then if you want to find the derivative of this thing, you take the constant out, find the derivative of the function, and you're done. And finally, the last rule basically says if you have the sum or the difference of two completely independent functions, then finding the derivative of the entire function amounts to finding the derivative of the first function, the derivative of the second function, and then adding or subtracting them based on what the example is. Well, those were the rules. We looked at some very elementary examples, and in this video we're going to look at some more complicated ones. So let's look at the first example here. We have y equals 2x. And you might not know what to do at first, but if you look carefully and you rewrite this as 2, well, think about it. Instead of dividing by something, can't you multiply by its reciprocal? And that's really the same thing. So the reciprocal of x is x to the negative 1. Okay, so it looks like we have a constant multiplied by a function, and I know how to find that derivative. Y prime is going to equal my constant 2 multiplied by the derivative of x to the negative 1, which is going to be negative 1 times x. Now, decrease negative 1 by 1, and that will be negative 2. Sometimes people, when this is a negative number, they forget what they're dealing with and they go the wrong way here. Just don't forget that you're always decreasing the power by 1. Okay, let's just simplify and we get y prime is equal to negative 2. Bring x back downstairs and we get negative 2 over x squared. Okay, the next example is pretty similar to the first example. If we rewrite f of z, I chose z just to show you that doesn't always have to be x, but I can rewrite f of z the following way. I could pull out this 4/5 and consider that 4/5 as a constant. Okay, so really I have 4/5 times z squared. This is just our constant times a function rule. So how do you find the derivative of f with respect to z? Well, it's going to be the constant multiplied by the derivative of z squared. And the derivative of z squared is 2z. Some simplifying gives us f prime of z equals 8/5 z. And you're done. Okay, the third example might look intimidating at first until you remember your rules for rational roots. And if you remember those, I can actually rewrite this so that it actually is a very nice thing to take the derivative of. Okay, let's first deal with the cube root here. The cube root, remember, is the same thing as raising something to the 1/3 power. So I'm going to take my x squared, and instead of taking the cube root of this, I'm going to raise it to the 1/3 power. Okay, well I can rewrite this, and that's going to be 2 times x to the 2/3 power. Okay, well, manipulating this even further, I can pull out this constant of 1/2, and I can now multiply it by x to the negative 2/3. Okay, I just basically took, and remember, instead of dividing by something, I'm multiplying by the reciprocal, and my laws of exponents say that if I bring this up into the numerator, I just negate the exponent. Okay, well this looks pretty familiar. I have a constant. I'm multiplying it by a function. Therefore, the derivative of this thing, the derivative of y with respect to x, or y prime, is going to be the constant times the exponent, which in this case is negative 2/3, times x. Now, decrease this negative 2/3 by 1. In other words, subtract 3/3 from it, and you should get 5/3. Okay, so here's your derivative. You're basically done, but now just some cleanup. And we will get y prime equals, I can multiply these two together to give negative, what would that be? Well, the looks like the 2's reduce, and I'm left with negative 1/3. And notice that x is being raised to a negative exponent, so if I bring him back downstairs, he becomes a positive 5/3. Now, you know, how far do you go? How far do you simplify? Well, it's a matter of preference. It's a matter of what your teacher likes, I suppose. I don't mind these rational exponents. If you want to change that to the cube root of x to the 5th, you can, but this is your derivative. You are done. Okay, the last and final example involves our sum and difference rules, and if I'm finding the derivative of f here, I notice that I have really three functions. I have a cubic function, a linear function, and this is really just a constant. Pi is just a constant. It's 3.14. So to find the derivative of this thing, I simply find the derivative of each function. So the derivative of this is going to be negative 2 times 3x squared. The derivative of this, well, think about it. What's the exponent on x here? It's just a 1. So if we brought him out front and decreased this power by 1, we would really get x to the 0 power. Now, some of you probably knew that the derivative was going to be 3, but this helps you see why it is. And then what's the derivative of pi? What's the derivative of a constant? Well, it's just 0. Okay, cleanup time. A little bit of algebra here, and we get negative 6 x squared plus 3, and you're done. Okay, so there's a look at using the 4 basic rules for differentiation. The trick to using those effectively is to try to rewrite your function in a way so that it looks a little bit more friendly to take the derivative of. Okay, look for more examples in the future. We'll see you around.